We are now live. Welcome, everybody. We are going to be talking about systems performance. Check this book out right here. Boom. Systems performance. I'm here now. Yeah, there's some people who are asking if the stream is postponed. We are here. So a little bit of a delay. My bad. Let's do tall, wide, medium. There we go. Good morning, everyone, or good afternoon, depending on where you're coming from. Happy that you are here. We'll let people just file in. We'll hang out a bit. Ooh, you know what, too? I figured out music for this. But anyway, for those just coming in, what we're doing is embarking on the journey of reading this book, which it's a thick boy right there. Look at that. It's like 800 plus pages. And today we're just going to talk a little bit about chapter 1 and just generally performance in software systems and computer systems. So that's the goal for today. Let me adjust this desk a little bit here. So good morning and welcome. I'm going to tell me how this sounds here. So we're going to do some music. And I think that's set up right. Tell me if you can hear that, because I don't have, I usually don't stream with like a headphone monitor or something. So if that's like good, tell me. If it's annoying, tell me. Oh, we got a little music going. So welcome. I hope you all have your coffees and you can join me. This is my second coffee of the day. A little bit of an iced espresso with milk. It's very good. Yeah, so what we're going to do today is talk about a new book. For those of you that have followed me for a while, you know that I like to go through different books related to systems, databases, performance. Where are my other books? They're usually around here. Oh, they're off screen. One moment. I'm going to go get these so we can talk about them. Be right back. There we go. I am back. So, I know I say this like almost every time, but little recap. Over the past year or so, I've done live streams where we've gone through these two books, and they're very good, both very much oriented around databases, data systems, how databases lay data out on disk, how to handle distributed transactions, how to scale databases with sharding, all of these kinds of things. Turn off the music. Oh, you don't like the music? Is it too loud? That's the thing that's hard for me to tell. Should I turn it off, or is it just too loud? Can't hear when music is on. I could turn it down. Is that better? A little bit lower there? Maybe I should just, I'm going to pull it up on my phone so I can hear how it sounds to the rest of the world. This is an experiment. I've wanted to like have the option to do background music, not necessarily like where I do it every time. Okay. Yeah, maybe it's a little bit loud. Okay, so I just turned it down a little bit more. We'll see how this sounds. Turn the music up, Daniel says. Yeah, maybe it's a little bit loud. Okay, so I just turned it down a little bit more. Okay, that might be a little too low. Okay. Sorry, you can probably hear yourself echoing in there. All right, we'll go with that. I want to experiment. We'll see. If you guys tell me it's terrible, but that may have been just too loud before, so I've got it down a little bit lower now. Yeah, there we go. Cool. So anyway, yes, Daniel's here. Welcome, Daniel. If you guys like performance discussions on Twitter, you know, seeing P99 graphs drop and interesting performance investigations and all of this, Daniel is the guy to talk about that. So go chat with him. So anyway, we've done those live streams. I kind of bounced around with different book ideas. There was another one that I was going to start, but I think what I've settled on, hopefully there's not another flip-flop, but I think what I've settled on is doing this one because it seems like it's a lot of things that are still very relevant to databases and data systems, which is what a lot of you know me for doing on here, right? And talking about the trade-offs of different like architectures of the performance and all of that. But this one, the focus is more on not like for one particular domain. It's like not just about databases. It's about generally how do you measure performance, how do you identify performance bottlenecks, and then how do you like basically if you were a full-time systems performance engineer, which Brendan Gregg, I believe he currently works at OpenAI as a performance engineer, and he worked at Netflix for many years as a performance engineer. But if your full-time job is like making sure performance is good or eliminating performance bottlenecks in big distributed systems, like places that he has worked at, this is the reference, right? It talks about the different tools, the different ways of visualizing data, the different techniques, the different places to look, the complexities of the system. And all of this is extremely relevant to databases and just like really any system, right? The small scale of like a piece of software running on one computer that maybe is going too slow, but could also be big distributed systems that power places like Netflix and like OpenAI, right? Where they're running thousands, tens of thousands, hundreds of thousands of servers. And how do we make the performance of these things good, where we're optimizing all of these CPU cycles that we have. So that's kind of the idea there. Bring me your graphs. Yeah, I wanted to actually I built a little while back a custom, I'm going to have to scroll a while through Twitter for this. Let's see, Benjay, Flame Graphs. Where is that tweet? Here we go. Let me change my view here. What? Try boosting this post. No. I tweeted about this a while ago, but basically, like, I think, actually, I don't know for sure. Brendan Gregg might have been the person to invent flame graphs as a tool for visualizing things. You guys can correct me if I'm wrong. But like flame graphs are one of the popular ways, and Daniel would know this, of like visualizing the performance and like where time is being spent in a piece of software. There's a difference between doing profiling and tracing, and this is often a way that people visualize profiles, which is basically as a software system is running, like in the example of this case here, make this bigger, this was an example. It was a tool that I downloaded an example from somewhere else, but I augmented it to have all these capabilities of being able to zoom in and kind of customize the view a little bit more. But a flame graph is basically a way to be able to view a sampling. So like you can, let's say, run a query on a database like Postgres, and then every millisecond you can sample what does the current call stack look like on a computer. And then if you gather 1,000 or 10,000 of these samples over the course of a second or 5 seconds or 10 seconds that the program is running, you then go visualize it as these stacks, flame graphs, to view how the performance works. So we'll talk about these a little bit more later on stream, and he'll talk about them a bunch in the book, of course. And this is a cool blog from Jan. Hope I'm saying his name right. Jan actually recently joined PlanetScale, so we have a flame graph expert here as well. But anyway, so this is a nice blog about how to do it with Postgres, and this is when I built my tool. It was inspired by this blog, and I kind of made some customizations to it. So anyway, let's see. Yeah, if you're just getting into your SRE career, this book might help. Yeah, for sure. So like, if you are a site reliability engineer, which again, Brendan Gregg, I've never met Brendan Gregg, but I've read a little bit about him in his book. He was an SRE for a period of his career too. And not always, but some of the time when you're dealing with a incident, right? Like a lot of what SREs do is they're working on the reliability of systems, but that also means you have to like address problems and incidents and server failure when it comes up, or servers being unexpectedly slow. Part of the role of an SRE is knowing how to assess and analyze performance, especially when that performance is slower than you expect. So how do you go in and like solve those problems quickly? Vivek says, so good you're doing this. Thank you, Vivek. I appreciate the repost earlier. Yeah. let's see, what are the requirements to follow this book? Well, I have not finished reading it yet, but hold on, where was my, I'm just gonna go back to, oh, I put it up in a new tab. The requirements for this book. I can't tell you a full answer because I haven't read it yet. It definitely is like, it's not for someone with no technical background, right? So this is something that you should probably like already have some experience as a software engineer or as someone who's like run databases before, or as, you know, even just experience in IT, even if you're not like a full-on software engineer, whatever. You should have some technical background and know like how computers work, how software works, and all of that. So Daniel says you can confirm it was Brendan. Yeah. Oh, so yeah, this was probably from a little bit ago. Showing flame graphs, but which tool is this? Go back here. Yeah, so this tool, and I may talk about it on stream a little bit later. This is a custom tool that I built. So there's already flame graph viewers out there that exist, so you can just grab traces and use off-the-shelf tools. But this is one that I took an example from a blog on the internet and I customized it to give it the ability to like, not all flame graphs give you this same capability of like hovering and the really nice zoom in, zoom out capabilities. Like the way that I built this one is actually where I can do these like click to drag zoom, kind of inspired by what we do at Planet Scale with Insights, right? We have these performance graphs that you can look at database and query performance, and we give you the ability to like click and drag to zoom in and zoom out. But then this actually remembers your stack too. So you can see like I zoomed in there and then I'm hovering and then I'm gonna zoom again. And now I'm hovering here. And then like, I think I made like as the escape character would be, you'd pop the stack back out to like the previous frame. So this is actually, and you know, most of this was just pretty much all of this was like, I took an existing example and I used cursor or whatever to augment it to do what I wanted to do. And that's the very cool thing about having all this power of AI tooling these days is like, I didn't care a whole ton in this case about the quality of the code because it was really just like a demo. It's not a tool that I use day in, day out. But even so, this is like a tool just for looking at performance traces. So it's not, you know, like a core piece of infrastructure that's being relied on where the code quality needs to be super high. This is just like a tool for visualizing some data. So as long as it's correct and represents things properly, in that case, I don't care as much about code quality. So I basically just, you know, had cursor do it. Main reason of here, I've never been able to finish this book personally. Well, we'll see if I'm able to. It's a long book. Talking about performance, and Daniel's here. Yeah, what I should do is one of these chapters, I should get Daniel to come on live. If you're not familiar, me and Sam and Simon do this P99 podcast, and Daniel came on one time, and that was fun. We got to talk about performance and all this stuff. So Daniel, I'll DM you. Maybe you can come on for one of these. Let's see. In my current job, I don't know if all this flame graph stuff is too distracting. In my current job, we don't have that much traffic, and we're not too concerned with performance since a standard Oracle or Postgres database configuration is enough. Yeah, let's get off the flame graph here. A little bit too much going on. Yeah, so in some cases, how concerned you should be about performance depends a lot on your requirements, right? Like you could be a company that's relatively small. You know, let's just focus on the database for a moment. Obviously, you can measure performance of your database and of your application servers and of your clients, and there's the whole many parts to the stack. But if we just think about the database, you might be at a point where you're like, okay, you have a database server, cost is not a concern yet, things are performing well enough, and there's other higher priorities like shipping your product faster because you're a young, fast-growing company, or maybe you don't care as much about performance. But then once all of a sudden your users 10x, right? And then you start looking at your database and going, before performance seemed okay, but now my tables are getting bigger, my data size is larger. And then you start realizing like, oh, I have some slow database queries. What's the problem? And maybe it's because the queries need to be optimized. Maybe it's because you need to use a different type of disk, right? Maybe it's the hardware that's more to blame. You know, there's a bunch of different factors. Maybe you just need to scale up your server. Maybe you need to do sharding. Maybe you need to, depending on how much control you have over the system, maybe you actually need to like tune different OS configurations or use a different underlying file system. So it kind of depends on like what stage you're at. And big companies will literally have engineers or whole teams of engineers whose whole job it is to like analyze and assess and improve performance of systems. Babe, wake up. Ben Dickin is on. Wake up. Time to wake up. Let's see. Is this a stack dump? Maybe we should jump into... We'll talk about flame graphs a little bit later. There's something else I want to talk about first that's a little bit higher level. But yeah, let's go over to... let's see. Chapter 1. Yeah, so this was my little outline of some of the stuff I wanted to talk about from Chapter 1. So, let's look here. Zoom in a little. So yeah, I read Chapter 1. So for those of you that want to follow along, this book is a little bit expensive. So I understand, it's close to $60. It's right around $60. But if you do want to follow along, I technically cannot like officially recommend it yet because I have not read the whole thing. But if you are interested in software performance, if you're interested in becoming either a performance engineer, a site reliability engineer, even a database engineer, anything that has to do with like you're dealing with critical systems in a company and where performance really matters, this kind of seems like the industry standard book for really learning how things work. So in that sense, I can recommend it. And so far, reading Chapter 1, it's good. So yes, so that's what I would say. Short answer from my explanation earlier, switch to planet scale. You know the drill. So from reading Chapter 1 is very high level. It's just kind of like giving you a little overview of, the different software stacks and where you can find performance issues and all these kind of things. So these were kind of some of my big takeaways of stuff I thought we would try to talk about today. One of them being flame graphs, which is related to profiling versus tracing, because usually you're using a flame graph with a profile, and tracing is something a little bit different, so we can talk about that. But the first thing I thought we would talk about, just broadly, is the software stack, because this is something... To some engineers, this is just like obvious because you've been working in this, in computers for such a long time. But for some, this might be a little bit of a newer thing or just like something you don't think about very often in terms of how these things work. So let's go talk about the software stack. And maybe I should do a little intro or something to this. So let's see. Oh, we have Tanel in here. That's cool. Let's see. Before we jump into that, Tanel has a very good blog post. And yes, I've, I don't know if I'm saying his name right. Again, I've never met Tanel, but he's got a lot of blogs and stuff about performance and, getting the most out of your disks in terms of IOPS and all that on LinkedIn and on X and on his website. So had a very good blog post about flame graph and Oracle databases performance troubleshooting. Oh, cool. Yeah. So check that blog out for that. So there's a lot of, there's people in the industry like a Brendan Gregg or like a Tanel who you can, go to their blogs or look at their books or look at their papers and publications, their talks online, if this is something that interests you. And the argument I would give going into this, well, maybe I should just start with the software stack. But the argument I would give going into this is that really performance should matter everywhere. And this is kind of especially true with, okay, now we have AIs, and AIs, like for a lot of us, pretty much write most of our code, right? Like I very rarely write code by hand anymore, and I'm not even like writing code all day, every day. I will sometimes write software for, maybe I'm running some database benchmarks and I need some scripts or something like that, right? Or I'm building like a demonstration of how something works in planet scale, and so I need to write code, but AI is generating most of my code. But it's like, okay, it's very easy, of course, to just have AI generate bad code, slow code, sloppy code, poorly structured code, unscalable code. And so when you take performance seriously and you know how performance works, that is something that even using AI, okay, like maybe the speed that you write lines of code at has 10x, there's a lot of things to still take very good care of. Some of that is the architecture of your applications. Is it scalable? Is it reusable? All of this. But another aspect of that is performance. And that's also, performance is not just about the code you write. It's also about, okay, you write some code, and then there's layers underneath like the operating system, and then there's the actual hardware, and how are all those things interfacing together, which is what we're about to talk about here. So maybe I should just shut up and talk about this. Okay. Wow, we got a lot of people in here. So my StreamYard tells me we're at 450, and we're only 20 minutes in. This is great. I think this will be a fun set of topics to talk about. So let me do a little bit of intro for this. How would I want to intro the software stack? You should be writing more performant software. No, that's not the intro that I want to do. Software? No. Man, this is hard. Like I'm coming up with like a good intro because I usually take these kinds of clips and I cut them and I put them on YouTube. So I want like a nice little intro to put at the beginning of these different segments. So software should be fast. Really nobody likes interacting with slow pieces of software, whether that's an application, a database, an app on your phone. So how do we measure and ensure that our software is quick, is performant? Let's take a look at the whole software stack, and all of these different components can contribute to how fast or how slow your software runs. Fast code is fun. There we go. That's what Daniel said. Measure before optimization. That's a good point. Okay, so let me jump over. So this is what we're going to talk about. The software stack is important to understand when you're thinking about what is the overall performance of a piece of software, because every component of this contributes to how fast or how slow it is. So what we're going to do to start, that line is too thick. This. So the first layer we're going to talk about at the very top is your application layer. So the application layer is, well, that's where your applications, why is that? Okay, hold on. I thought when I do this here, why can I not? Yeah, okay, that's together. Sorry. I haven't used, I don't know why Excalibur did that. So let's try this again. So the software stack. We need to understand every component of the software stack in order to ensure that we kind of have a good mental picture of all the components of our system and how each one can impact performance. So the first thing we're going to talk about is the application layer. So every time when you're doing stuff on your computer, right? I have OBS open right now. That is an application running on my operating system. I have my browser open right now. That's an application running on here. I have a couple other pieces of software for, doing audio stuff for these streams. So each of these are apps that are running on my system. And obviously each of these have like code that was written to power them, right? Like modern browsers that are Chromium based, literally, I think Chromium is like 1 million lines of code, right? So some of these are very complex pieces of software, some are simple, but this is the software that is running on your computer, right? And of course you can write that software in efficient ways and inefficient ways, so there's a lot of care that needs to go in how you write that. But there's a lot of other components here too, and I'm taking this diagram approximately from the book. So some applications are also interfacing with a database. And it depends, like, what do we mean by database here? This could be an application is actually making remote requests, like a local app on your computer is making remote requests to a database somewhere. This could be a local database that's on your computer, like a SQLite database that it's storing things in. Database could be as simple as a CSV file on disk. Or this could be a web app where the app is running in your browser and then it connects to the back end of the application, and then that back end is connecting to a database. So there's lots of different architectures here. But the database in itself, plus all of the networking that goes into sending and receiving requests, there's a lot of performance tied up just in that concept. And then, let's see, we have, so this is sort of like the way that we want to think about this is oops, this here. Oh, I don't want that. I want that to be solid. And this is user land. So I'm going to just type a little label here. User land. And if you're familiar with operating systems and how operating systems work, this is like applications, and the database is also an application run in the user space, right? Rather than being run as a part of the actual operating system or the kernel. So then below this, we might need to zoom out a little bit to make more space for the other components. So hold on. Then we need to go into some other components. So below this, we have our system libraries. So when you are on Mac OS, you're on Windows, you're on Linux, Ubuntu, whatever, right? There's different libraries that are either pre-installed or you can install as like third-party things. But these are things that a lot of applications are relying on, right? Your database, your app that you write, my web browser, whatever, might be relying on either pre-installed libraries on this operating system or just libraries that might have been installed after the fact, right? But it's like your application is not actually in control of these, even though it relies on it. So this is another thing to consider, right? It's like you might have written your application code all very nice and good, so it's very fast and performant. But then if you're relying on a library that's built into Mac OS and that's a slow library, you can have performance issues, right? Okay, so then the next layer down here, and this is where we start to cross into the boundary that goes into the operating system, but is system calls. And so this is yet another thing where not everybody is super familiar with how operating systems work. So there's kind of a balance personally here with like how much do I want to talk about operating systems. But system calls, most operating systems have, I don't know the current number, right? But maybe it's 50 or 100 or whatever. But these are essentially how you transition the boundary from code that is just running in user space to then code that is running, that is going to basically go into your operating system and start doing things. And you need to do system calls to do things like interface and send content over a network, or make requests to your file system, or page content into memory, right? Things like that. So now we are at our system call layer, and below this is where the fun begins. Actually, all of these components are pretty fun, but the kernel. Okay, so this graph might end up being a little taller than I thought. So we've got to zoom out a little bit more. Hopefully you'll all be able to see that just fine. But the kernel down here, and within the kernel, there's a bunch of different, the kernel basically means this is like the core component of the operating system that handles essentially the interface or the abstraction that's directly abstracting the CPU and the RAM and the hard drives and the network cards and all of that underneath the computer that you're running on, right? And there's a lot of software engineers that I think that don't spend a lot of time thinking about the hardware. Like obviously most software engineers know the basics of how a CPU works and how RAM works and how disks work and that disks are slower than RAM and all of these kind of things. But there actually can be things that you can do and write code differently up at your application layer that will impact and writing code differently up here can utilize the components of the kernel better or worse. So the thread, or I guess really this would probably more like the proc scheduler, right? So there's, on operating systems, right, there can be tens or hundreds of processes running at the same time. So there's like a component in the kernel that's responsible for scheduling which pieces of software can run when. There is the file system. So you have a hard drive, you have files on it, but there's an abstraction called a file system which controls the organization and when things get written and how things are read and written to this device that you have, right? Like your SSD or your HDD, your network card or your network stack, virtual memory. So this is the system that manages like how your virtual memory is like every computer has RAM that it's operating in, but there needs to be an interface for managing which processes can use or see what memory. And so virtual memory is how this is handled on pretty much all modern systems. So your system calls are what allow your applications or your database and your libraries to be able to actually go start interfacing with the operating system as a whole. I'm going to group this together. And so that is our kernel. And then finally, our like very bottom layer that we can think about is simply the hardware devices, right? So this is your CPU, this is your RAM, this is your solid state disk, this might be your network attached disk. You know, if you're running in the cloud, this would be your EBS volume. This could be S3, right? I mean, technically S3 has a software interface on top of it, so that's, I think I took the explanation a little bit too far there. So really what this means though, because if you send something off to like S3, it's still going through an operating system. So really what this means here is your actual hardware, your CPU that's inside of your laptop, your hard drive disk, your RAM. And so those things get interfaced, generally speaking. If you're writing code that needs to access those, it's actually going through the kernel via system calls and then giving commands to the hardware to read some data from disk, to write data, to load something into RAM, all these kind of things. Okay. So let's look at this picture here, and now we think about, there's a lot of components here. And sometimes software engineers are only thinking about this layer right here when it comes to performance. For one, some software engineers aren't even paying attention to performance, and they're building apps that are slow. But even if you are paying attention to that, a lot of times when you're building a piece of software, you're just writing the code that is up here at this application layer. And that's fine. But if you know your code really well, but if you don't have a good understanding of how does the database I'm using work? How does Postgres work? How does SQLite work? How does MySQL work? If you don't know the libraries that you're depending on and know how well performance optimized they are, there's room for performance problems there. You don't have to be an expert at the kernel, but if you don't know, like there are different ways of, for example, doing I/O communication between the software that's running and the hardware, right? Like there's different interfaces that the kernel provides for example, when you write something to disk, are you f-syncing that right away where it actually does confirms that it has been written, the bytes onto the hardware device? Or are you doing a non-f-synced write that allows your program to say, hey, write this to disk and get a response back saying, I've completed that task, but it might not actually be on the device, which gains you performance, but you now also have a risk of data loss in some small window between when that actually gets onto your device. So there's a really important thing if you really want to get good at writing high-performance software, you should actually understand this entire software stack. And that's one of the points that is made in this systems performance book in the first chapter is sometimes a performance problem is, you know, you might be responsible for this application, but sometimes the performance problem is actually here, right? The performance problem could be in your system libraries, or it could be in like you're using, you know, a file system that is suboptimal. You could be using a different file system for the type of work that you're doing that would make performance be better. It could literally be a hardware issue, right? Like maybe a hard drive has degraded performance because the SSD is old and, you know, there's starting to be some of the pages and sectors that are starting to fail because it's old. And sometimes it's actually the interaction of how you wrote your application code that happens to combine with what system libraries you're using, that happens to combine with a hardware device, or even it could be a different piece of software running on the same computer that is like conflicting with the performance of the, you know, two applications are competing for resources and that impacts performance. So you can't just think about, is the code that I wrote, like, does it use the right algorithms? You know, is it using good software principles? That's important, but there's actually like so many other places where performance can become a problem. And so this is part of what is going to be covered in this book, right? Is Brendan is going to go through a lot of these different things. Like, for example, I believe there's going to be some stuff in the book, he says, where we talk about operating systems and how they work. Now, there's definitely books or you can just go look at the source code or whatever, where you can learn much more in-depth details about operating systems. We're not going to cover every little thing in this book, but this is a way to get familiar with how it works, and then you're equipped with tools to be able to help you identify, hey, is the problem in my application or is the problem elsewhere? Let's see, a couple of questions. Thank you for the content. I find the music distracting. Let me go look again at what this is like live here. The music is experimental. I will definitely give you that. I find the music distracting. Let me go look again. This is like live here. The music is I guess it depends on what song is playing at the moment. I'm going to keep it going. We'll see. Give me feedback after. I want to give it a good run. Thank you for the content. Hey, Ben. Hello. VM isn't in the kernel. Oh, well, this VM was not virtual machine. It's virtual memory. So maybe you were thinking I meant virtual machine, potentially. I don't know. It was ambiguous there. It's like computational complexity. If a library has a higher complexity, say O(n)², it hurts your overall complexity. Yeah, right? So there could be like complexity or performance issues buried in a system library that you don't actually know how it performs, and then that can be at fault. Let's see, IOU ring. Yeah, so I think this is going back to earlier when I was talking about an operating system can have different interfaces for interacting with the underlying devices, and IOU ring is a good example of this. That's sort of a relatively newer interface that's come up over the past few years, and some pieces of software are starting to leverage that more. Like Postgres 18, when that came out, started to adopt IOU ring for some IO stuff, and then when Postgres 19 comes out, it's going to start adopting it more, right? And so like that is something that presumably is going to, in some cases, help make IO performance faster in Postgres. So yeah, cool. Okay, so hopefully that explanation helps, and this gives a really good frame of reference. Let me think, what do I want to say here? So hopefully that explanation helps and gives you a good frame of reference for thinking about performance, and when you're digging into performance problems, all of the different possible places that it could come from. And the reality is there's even some things that are not pictured here that have an impact as well. So this is mostly just looking at the state of a single system, a single computer, right? But the reality is what you also often have too in large-scale distributed systems is you have network effects, right? So you have this, but then there's also like your, let's call this your app server, right? And so then we've got an application server, and then I've got my database server, and then I've got my, I don't know, your queue server, and then this goes off to your, maybe your analytics database. So this is, you know, adding complexity, right? Every system has different levels of complexity, depends on the tools you're using, depends on the scale you're operating at, all these kind of things. But just to kind of show off the complexity, right? This is like perhaps the performance of a single system, but then you could have it where like a local application is actually sending off requests to some remote app server. And this app server in itself has this stack of complexity with system libraries and system calls and an operating system that it's running on and a disk. And then this app server might be making requests to a database. And so there's data flowing back and forth between these two. And of course, the app needs to be able to respond to the application. Although technically I have these arrows here, but really these arrows could actually, I could be drawing these from the kernel or some other layer that's handling the actual direct network requests. So maybe I'll just make these arrows sort of arbitrarily going like this, right, to and from that. But then also there is, oops. Then also your app server might be sending stuff off to a queue, right? So there might be a job queue that it's sending jobs off to. And then in addition to that, your app server could be sending things to the queue that then sends things to an analytics database, or your app server could be connecting directly to an analytics database to pass information off there to store those things for admin dashboards. And then each one of these components has these complexities. Like if you're running Postgres, that is still running on top of an operating system that has a file system and is making system calls. If you are running a queue, right? If you're running Kafka or something like that, that is still running on a system with a hard drive and with an operating system and so on and so forth. So really, then when you're debugging performance problems or issues, you not only have to understand the software stack of a single node within this computing system, but you may have performance problems here, or you might have performance problems that are related to how your application wrote code, which then it's sending queries off to the database server and the database seems slow, but it might not be that your database needs to be tuned. Like sometimes the solution is, oh, I need to change some configurations in my database server so it performs better. Or it could be your database server is completely fine and it's actually just you need to change the way you wrote your code in your application layer, or change the system library that you're using so that when it sends off queries to the database server, those are faster queries. So it's these big complicated systems. And this is one of the things that's so fun about it. And I imagine too, I've never been like, I guess early in my career, a big part of my role was actually performance, a little bit different than like what Brendan Gregg was, but I was doing a lot of writing static and dynamic performance analysis tools to measure the performance of databases or to identify places where we could apply optimizations to the database. So I wrote lots of tools with Clang and LLVM, with Intel Pin, that's like a dynamic instrumentation library. I even used some GDB, or really RR, which I think is a wrapper around GDB, which can do reverse debugging. So basically reverse code execution in a debugger. So I was doing a lot of this kind of stuff, right? So different than, it wasn't like I was logging into production systems and assessing performance. It was more trying to find places where we could optimize a database, but not like in production. So different kind of experience, but I do have experience building tools to find places where performance can be improved. And it's a fun, very complicated thing, right? Even when you're just looking at one piece of software, let alone the whole picture of everything. And I imagine if you're in 2026 and you're a performance engineer, the added capability of being able to use AI to automatically like look at ingest logs, ingest trace information, build visualizations for you, kind of do some assessment and thinking and correlation for you, can probably let you work faster on these kind of things. But it is very cool, right, to be able to like look at a whole system and then figure out how do I make the performance better. So that's the software stack. You should know it. You should understand what each component does and doesn't contribute to performance. And once you do, that will allow you to better investigate, measure, and resolve performance issues in the software that you are running and managing. So let's look here. A couple of questions. Can you give me an example of one system library? Yeah, well, I mean, when you, like on just a standard sort of base like Linux installation, like let's say you installed Ubuntu on a server, right? There are some things that are a core part of the kernel of that operating system, the Linux operating system. But then there are some things that are system libraries that are just installed, like probably an example of this would be the C standard library. There's a bunch of functions that, if you were writing C code, that do things like different, string comparisons or different kinds of just functionality, right? Like it's a standard library to do a lot of basic stuff. And so that is something that if your software is relying on the C standard library to have functionality, again, the C standard library is pretty hardened. It's been around for a long time. But if you don't understand the algorithms and the performance behind how each of those functions work, then you could get yourself into a situation where things are performing poorly and you won't know why until you actually understand it or measure it. Let's see, the throughput of a system is determined by the bottleneck. So we don't spend too much effort in the wrong direction once we are in a solid position. Yeah. So a big part of doing performance stuff like this is finding the bottlenecks. And sometimes you can't just like know what the bottleneck is. A big part of what this book talks about is how do you use different tools that either are built in to like Unix systems or that you download. But there's a bunch of tools to allow you to trace and measure and find where the performance issues are. Please keep this recording on YouTube. That's the plan. At some point I might stop doing that, but so far, most of the live streams I do, I leave the recordings up on YouTube. And then you'll also see me on stream sometimes like retake an intro or something, because I usually like to take these and chop them up and make them standalone YouTube videos, because not everybody can make the stream. It's a little bit easier to find and digest in nice little chunks sometimes. Not everybody wants to sit online for a super long time. So yeah. Let's see. I'm just looking around. Just hang out for a little bit. Check X notifications here. Let's just pull it up over here. Mickey says, I'm ready, Professor. Learn, teach, learn, teach. Oh, that's too nice to say. Do you guys see the meeting balls? Shipping speed. Let's just enjoy this for a moment here. We should do a whole stream just on this. Let that sink in. Wait, what is going on with? Oh, I see that's the aspect ratio. Yeah. How fast you can ship with a lot of meetings and without a lot of meetings makes a big difference. This is something I'm learning all the time, because there's a lot of meetings either that I have to be in or should be in, or that I organize with other people at Planet Scale. And we got to figure out how to use the time in meetings wisely. You shouldn't have 0 meetings. This is obviously exaggerating a little bit. Some meetings are good, but one of the big parts of Planet Scale's culture is like, basically, let's not waste time, right? So some meetings are very critical to like figure things out, to collaborate with people. It's important to get that face-to-face time. But there's a lot of organizations where there's just half, a third, 80%, 90% of meetings are basically just wasted time. And if you kind of think about the efficiency of how you're working, you can restructure things to get a lot more done in the same amount of time. And some of this has to do with teams being too big. Some of this has to do with politics and bureaucracy. Some of it has to do with just not being aware of the possibilities that you can, the things that you can achieve without being bottlenecked by a bunch of meetings. Okay, I like this diagram. I like this graph. This is a good one here. You ever write a graph and you're just like, that looks good. That's what we did here. Oh, I need to move my head up there so that we're not. There we go. Okay. Ah, you still see the purple a little bit. There we go. So, wait, I thought this, why is this an untitled scene? I thought I had titled this. So this is our systems performance chapter 1. Okay. So going back over here, let me move this over a little bit more. Get out of the way. So we talked about the software stack. That was one of the big things of just like going into learning about systems. You should understand. Obviously, what I just taught you isn't going to actually teach you fully how to do it. Some of that stuff you would learn by reading this book. Some of it you just need to learn by doing and building and with experience. Some of it you can learn with other resources that there are online or by reading man pages and all that. So let's see. Let's talk about, I'm going to draw a graph ahead of time here. So there's an interesting, in the book, there is an interesting case study. Let's see. There's an interesting case study in the book that really illustrates nicely sort of how complicated performance tuning and performance engineering can be. I'm going to go grab this. We'll just use this as like a starting point here. Okay. Oh no, what just happened? Okay. Let's see. I need to go look at what the questions are. Okay. Let's see. Thanks for the explanation. Great content. Ben, do you ship at planet scale? Of course I do. We all ship at planet scale. One of the things I will say, so I don't really work on the products itself, at least as like building the products. So we have extremely talented engineering teams. Most of the engineers at Planet Scale are much more talented than me as engineers. And so they do most of the actual building, whether it is building of the sort of operators and orchestration of the databases themselves, building like the different product surfaces, right? Like the application, the command line interface, the APIs. There's many different aspects of running databases at scale and reliably, building Vitesse, building Niki, which are our like sharded products. But I do obviously interface with them a lot on a daily basis and help influence the direction of the product. And a lot of that comes from being able to like be out and interacting with people and customers and people using it, and then being able to like bring feedback or bring ideas. Or another thing I do sometimes is run benchmarks on things. So if I identify performance issues, I will sometimes pass that along and create an issue and say, hey, I identified this could be better, this could be improved. And then often someone who knows more about Postgres or MySQL has to come check my work and make sure I actually found a real performance issue, or if it's just, some other cause, right? And this is the thing about performance. It's like, it's not always obvious what the real true cause of a performance issue is. And of course, I ship lots of, not the product itself, but just lots of other things, right? So I do, and the people who I work with, right? Simeon and Josh and Chris and all that, right? Between all of us, we do lots of content creation, so videos and live streams. We write blogs. We help work on and maintain and build out documentation for our products. We test products out. We give product feedback. We interface with customers. We do all of this kind of stuff. So it's shipping, but it's a different kind of shipping. Very important side of every company. I think it's easy for some companies who are in the dev tools engineering space to get too focused on just build the product, which of course you have to have a great product. That's very important, but you also have to be able to talk about your product, communicate your product, explain your product, show the value of your product. I think that's one of the big things. Differentiate your product, and that has a lot to do with not just building it, but how do you communicate about it? How are you expressing to the world what your product is and why you should use it? So that is, I mean, that's one way to think about like the role of, my role is, let's go over here. Since we're not starting that yet. More broadly, yeah, can you talk about your work at PlanetScale? So my role at PlanetScale is developer education. Some companies call this developer education. Some call it developer experience, developer advocacy. That's a little bit different. Some of these names aren't even all that great, but really what it comes down to is companies like PlanetScale, something that is very valuable to have is someone who both knows the technology well and also knows how to communicate about that technology, right? This is, probably a lot of us here from our youths, right? Like the skill of communication is very important, but especially in the world of engineering, we don't always get good opportunities to practice that, to test our skills at that. And fortunately, I have had a lot of opportunity to do that over the years. I have a background for a good chunk of my career so far. I was actually in a faculty member at a computer science department, and I was going up, whether in person or in some cases online, making videos and teaching people everything from intro programming in Python to how to build web applications to like systems programming with C, mobile app programming, right? A number of different like courses that I got to teach. And I make no claims that I'm some kind of perfect communicator, but like, especially for people in our field where we spend most of our days just staring at our computers, it's really good to force yourself to practice communicating about products and about value and about technical things. So I've had a lot of experience doing that. And so that is something that's extremely valuable. And so basically the way to like high level summarize what I do, and again, what the other people in this team at PlanetScale do, is how do we communicate both broadly interesting stuff about databases, about systems, about reliability, about performance, and then also more specifically bringing it down a level, how do we communicate those things specifically about our product? How performant are PlanetScale databases? What are the features of PlanetScale databases? Why should you, an engineer building a product, run your databases on PlanetScale? And there's so many different ways to do that, so many different complexities and nuances to doing that well. And that's what I spend a lot of time thinking about. And not just how you do it in terms of like the words that you use to explain and teach, but also broadly, like what are your strategies for, in my head, since I think about PlanetScale all day, it's like, it's easy to get into this mindset of, everybody knows what PlanetScale is. But the reality is there's probably like only 0.001% of the humans on Earth actually have heard of PlanetScale. And then even if we only talk about like technical people and engineers and stuff, it might only be, whatever, 1% or 5% or 10%, whatever it is. I don't know the exact number, but some relatively small percentage of all engineers know what PlanetScale is. So how do you create things that lots of people will actually see and enjoy and learn from? So yeah, that is my goal and my mission at PlanetScale. It's good if you're working at a job, you should have a mission, right? Shouldn't just treat it as, I go in, I do my thing, and I leave. Like, you should have missions that you are on, and always be thinking about how you can achieve those goals. Let's see. I bought a book a year ago, and I'm thinking I might follow the series. You should do it. So as a reminder, we'll switch back to it in a few minutes. We're just hanging out here a little bit. But what we're embarking on is a live stream series going over all the chapters of this book. And it is a pretty thick and big book, over 800 pages, including the appendix and everything. So it could take us a while, or we may not make it through every chapter of the book. There are some chapters that are more like very specifically about certain tools for measurement, and so we'll see how far we get, but I do want to spend time on these streams talking about performance and systems. Let's see, someone asked, hold on. This is what do I ship at PlanetScale? Balls don't count. That counts, okay? The balls take some effort to put out there. How do you gain experience in distributed systems and these types of performance challenges if in your job you don't have it? So in the meantime, like if you have a job where you don't have opportunity, one is make the opportunity. Like just because your job role might not entail being a performance engineer, you can go above and beyond and try to identify and solve performance problems. Another possibility is try to get into a role where that is officially a part of the job requirement. And then in the meantime, while you're looking to get those kind of roles, applying for those kind of roles, talking to people about those kind of roles, get good at all of the tooling and things that you need to know surrounding performance of systems. Am I a forward deployed engineer? No, not really. Forward deployed engineers are very important though. Thank you for the great work. I'm a data scientist student and I'm learning a lot from your material. Would love some insights on job scenery in 2026. Which steps do you recommend? So everyone's got different opinions on this. I'm not going to claim that I have the perfect answers to finding jobs or the industry future with AI and all of that. I have some opinions, but take them as opinions, not hard and fast facts. I think there's always going to be demand for people that like computers, are good at computers, are fascinated by computers, and are good at getting computers to do things. The landscape of what those jobs look like, of how many of those jobs that there are, of the kinds of things that you're going to be doing, are changing and probably are going to continue to change over the course of the next couple years as LLMs and AI models and agents become more powerful and more capable, and just as we as humans learn how to be more effective with them. Right now, there's still tons of people just experimenting. What are the best ways to use AI to write code or to help resolve issues or to help identify performance problems, or applying them to other fields, right? Medicine, law, all of this kind of stuff. So one of the big things is learn the core principles of data systems and performance and computer science. Also learn how to get very good with AI tools. And over time, the big thing is growth mindset. Be willing to change, be willing to learn new tools, new systems, and also just be willing to work very hard. Because you got to work hard to get into certain kinds of jobs or certain kind of roles or certain kind of companies. And also show your work, right? Hopefully it's good work. You should only show it if it's good presentable work. But if you have good presentable work, whether that's software projects or tools or visualizations or videos or tutorials or whatever it is, show that work off to the world on your websites, on socials, wherever you may be. It's kind of fun just chilling and answering questions. We'll get back to another section here soon. What is the best book to learn trace bottleneck in backend app? That is, you should read this book, because this book talks about a bunch of tools and it depends. Are you going to do sampling? Are you going to do sampling and profiling? Are you going to do tracing? There's frameworks like eBPF. There's, strace and ftrace, and there's a bunch of different tools, right? And I'm not even an expert on all of these. So this is why we're reading the book together. Oh, interesting. Okay. At work, we are using Ghost. I can imagine replacing MySQL because of it. What is the alternative for PG of MongoDB? This is a very good question. Thank you for asking this. So one of the things that I absolutely love about working at PlanetScale is we have just some really talented people here. So you mentioned Ghost, and I would be very curious, Mohammed, if you're allowed to say what company you work at that is using Ghost. So PlanetScale employs the inventor of Ghost, or one of them. There was a few people, but the main person who built Ghost in its first couple of years is a guy named Shlomi, who was an engineer at GitHub, who was an engineer doing databases at GitHub, doing databases at Booking.com. I think he worked for Oracle for a while, actually working on MySQL core. And he now works at PlanetScale and does stuff. He works on Vitess, he works on Niki, and also, I can't say details as to when, but soon we are bringing some of the same functionality that you love from Vitess, which is our whole branching and deploy request way of working for doing schema migration safely and powerfully and with zero downtime. We're bringing that capability to Postgres as well. But basically a lot of the principles of how that currently works in Vitesse, it's Vitesse features, but a lot of that was inspired by the work, whatever, a decade plus ago on Ghost for doing. Ghost, by the way, stands for GitHub Online Schema Changes, because it was a tool that was built by GitHub engineers for doing online schema changes, meaning changing the schema of your relational database online without any downtime, which a decade ago or 15 years ago, whenever it first came out, was a really big problem. And it still is a really big problem. In fact, I was talking with Shlomi a couple of months ago, and he's, essentially one of, if not the world expert in doing schema changes on database in production, right? And he was basically talking about how he spent most of his career in the MySQL world, and the past year or so has been doing more in Postgres. And he was talking about how just the state of online schema changes in Postgres is it's like people are in the Stone Age, right? There's like so many better tools and ways of doing it that have been developed in MySQL, and we have a really high standard of the kind of tooling we want to provide to our customers to do things like this, and that will be coming. So stay tuned there. Let's see if you said. Okay, I didn't hear a reply for where you work. Again, I'm very curious. There's lots of companies that use Ghost, but I'm just kind of curious, who today is still using Ghost and how does it look like and all that. Let's just go to GitHub, GHOST. Yeah, so this is GitHub's online schema change tool. When did this come out? How do you see, is there a way just here to see how old a repo, oh shoot, I'm not sharing. Is there a way to see how old a repo is? A lot of commits. Let's see, let's just go to the releases. I don't know if they've been doing releases. So the first release was in 2016. It probably obviously started work on it before then, but this was like a pre-production release. So yeah, it started about a decade ago. And you can see there's Shlomi, and if you actually go to the code, last commit was 2 hours ago. So it's still being used, still being maintained, but the #1 contributor, boom, Shlomi, and actually the second contributor is also somebody who is at Planet Scale, and helps maintain the tests, which is a very powerful piece of software. So anyway, that is one of the cool things about being at Planet Scale is just there's this incredibly high bar of like engineering talent and excellence, and it's very cool to be able to be someone who, even though my job isn't like building Vitesse or building online schema changes or building Niki on a day-to-day basis, I get to hang out in Slack and in meetings with all of these people and learn from them. So always be learning. How do you get engineering leadership? How do you get engineering leadership to understand that database architecture and governance improve development velocity rather than slow it down? This is one of the big things that we sort of harp on at Planet Scale, right? Like Planet Scale is pretty much by far the absolute best way to run a MySQL database, because every MySQL database on Planet Scale is powered by Vitesse. And so not only do you get MySQL, but you get all of the high availability benefits of Vitesse and the online schema changes of Vitesse and the sharding capabilities of Vitesse, right? And we have a really excellent regular Postgres product right now, which is amazing. But then also building Niki is like we're bringing a lot of those same like ultra powerful capabilities from Vitesse to the Postgres world. And basically once both of those are out, I mean, Vitesse already is, right? But once both of those are out in the world as products, it's a no-brainer, right? Like Planet Scale is the best place to run a MySQL database or a Postgres database because it's performant, it's reliable, and it's scalable. And you also can come in knowing that like the technology, the implementation, the operating, et cetera, is backed by some of the most talented database people out there. When you read dense tech books or blogs, what's your process to actually ingest the info? Do you stop and run experiments or try to build a mental model first? It depends. Oftentimes I'm in a time crunch, or it's like if I just had like 10,000 hours to just sit and read this book, that'd be cool, but I don't have that kind of time, right? So oftentimes if there's something I don't understand, whether it's from a book like this or an academic paper or a blog post, usually I don't have the time to like go off and do some deep experiments or test things out for a couple hours or run benchmarks or whatever. So usually it's just like, hey, I'll understand as much as I can in, maybe I've dedicated an hour to do some reading. And I have a certain goal of, I want to finish a chapter in this time, or I want to finish this paper in this amount of time. And it's like, okay, yeah, there may have been a few details of that paper or of that chapter that I didn't quite get. And whether or not you should get hung up on those details depends a lot. If you're doing it for more general learning, probably don't want to get hung up on those details. If, on the other hand, you're doing it for the sake of, if you're doing the learning for the sake of just like, for example, maybe you're reading the paper, an academic paper on how to build B trees. If you're actually an engineer who's like, I'm going to go build a B tree storage engine for a database, then you should probably understand very deeply how every aspect of a B tree works. So if you don't understand something, you should stop and reread it and test it and diagram it and try something out. But if you're reading it more to understand the high level performance characteristics and structure, you probably shouldn't get hung up on every little detail. Is this the book recommended to you? I'm not going to click on the link, but that looks like it. Systems Performance by Brendan Gregg. Yeah, that's the one that we are talking about today and that we were going over. Let's see. Okay, so the person got back. I work at DigiKala, biggest e-commerce in the Middle East. Amazon equivalent. Okay, tables are in the terabytes, all MySQL and ProxySQL. Yeah, so that is like exactly the kind of organization that would use Ghost, right? Your large scale MySQL. Let's see, you've got individual tables that are multiple terabytes in size. And I don't know if you're doing sharding or anything like that, but yeah, especially when you have very large tables and you want to deploy schema changes, which often require rebuilding tables in some cases, you definitely want a tool like Ghost or Vitesse, PlanetScale with online schema changes, right? Given that you seem like a perfect fit for this, while you're here, I would recommend you check out Vitesse and PlanetScale, because basically the combination that we run with Vitesse, which is an open source project, MySQL is obviously open source. We have our own proprietary operators and sort of way of running infrastructure and our app layer and all of that on top of it. But all those things combined, and then when using it in PlanetScale, you get basically the capabilities that Ghost gives you through our product via Vitesse to do online schema changes and to be able to do reverts and all of that. So you should check it out or DM me or something. Quick plug. Yeah, I've got to plug every once in a while, but it's just too perfect. I mean, Ghost is an incredibly powerful tool, but essentially PlanetScale plus Vitesse is like the evolution of Ghost, a more modern, better product version of what Ghost is. Okay, so let's see. One real quick thing. I'll switch back to talking about the book after this. Would be great to have someone from the team working on Neki to share how they're approaching solving scaling challenges for Postgres. Will Neki be open source? It would be very cool to have some of the Neki team on. We've got incredibly talented people working on it. Probably at some point, maybe more when we're in the future, when we're a little bit more public about it. I think I would love to get some of the people who are more closely involved in actually building it to come on and just like talk about, hey, what were the most interesting challenges while developing it? What were the most interesting architectural decisions? How did you measure performance? All those kind of things would be fun. I agree. Okay, so sorry I didn't get to every question. I just want to make sure we have some time to talk about other stream stuff. But this, I'm liking this. This is fun. It's kind of interesting that they have the like World Cup scores right here. I have not been watching much World Cup other than watching a little bit at the PlanetScale office because we had some up there. Boom, boom. Put this on a billboard. There we go. Let's just repost that one. Ooh, you know what? That would be so sick. What if I rented a billboard in San Francisco and just put this on it? Dude, how cool would that be? Like a digital billboard, right? Where you can actually have like a video or something. Ugh. Daniel, you're giving me ideas. That would be hilarious. The funny thing is, like in most cities around the world, nobody would like get it, but because most of the people follow me are like tech people, putting this on a billboard in San Francisco, people would be like, ah, I know where that's from. Okay. Anyway, good updates. Let's go back to here. What a lenticular billboard. Hey, Jonathan. Welcome to the stream. I did not know that's what it was called, but good to know. Lenticular billboard. Instead of a green ball, it's the Planet Scale logo. Now we're thinking. Now we're talking. All right. Time to hit up Holly and ask her what the billboard budget is. Yo. Okay. So let's talk about, there's so much, I don't know, it's a good stream. So much energy. There's a lot of you hanging out here. It's good. So I just kind of want to chat. But we should switch gears a little bit to talking about other database stuff. So let me think of a good intro for this while I sip some water here. How's the music volume? Is it good, too low, too high? Again, the music is an experiment. We'll see if it sticks around. I actually can't even hear it right now. I need to get a better setup with like a monitor where I can hear it while I'm streaming, but I don't like wearing headphones while I'm streaming. So I don't know, got to figure it out, but. All right, so let's try and do a little intro here. Sometimes databases are just mysteriously slow. And the question is, when something's slow and you don't know why, what are the steps that you're going to take to figure it out and then solve the problem? So we're going to walk through a scenario of a database being slow and then think through what are the steps and the ways in which we would identify what the root cause is. So let's jump in and take a look. Oh yeah, maybe more people are on the stream today because of it being a holiday. And maybe more people can hang out. That's a good point. So here's the scenario. We have a mysterious, slow database. And let's say you're a performance engineer. You're someone being called in to help solve this problem. So you, from your other engineering teams, other people inside your organization, a customer, whatever it is, you're getting reports of the disk that your database is reading things from being slow. And this happened all of a sudden. This only happened recently, right? So what we're going to imagine is, say we have I'll move this over a little bit so it's not in the way. So we have a graph of like, we'll call this our query latency. And let's call it our our slow query latency, right? So sometimes what some databases have is support for, oh shoot, I did not mean for that. Do a new thing here. Our like P99. So what some databases have, we're gonna hold on. What we're gonna do is look at the graph of our P99. And so there's different ways you can assess the performance of queries. You can look at P50, P99, your max query latency, your slow queries. But let's say your P99 on your database was, we'll just draw a line, right? Like it was low, right? Let's, in this view of this diagram here is like a 1 week view of your database. So it was very low, right? Your database queries were nice and fast, right? Maybe your P99 was just like 5 milliseconds or a couple milliseconds. Then all of a sudden, like 2 days ago, this P99 jumps up. And instead of being 2 milliseconds, it's like now 50 milliseconds, 100 milliseconds, 500 milliseconds. Or in this case, the example that we're talking about is some databases have this idea of a slow query log, where you can have a dedicated log that only shows queries that execute above a particular threshold of speed. And let's say we had our slow query log set to 1 second, 1,000 milliseconds. And so maybe all of a sudden before, there were no queries in our slow query log. And then all of a sudden the past 2 days, we have tens or dozens or hundreds of slow queries showing up in our log every minute. Okay, so we have this clear performance issue. And what you're being told is that, hey, some engineers, we looked in our performance dashboards, we looked in Grafana or Planet Scale Insights or whatever your dashboards are, right, to look at, you know, query performance and all this kind of stuff. And you can see that the CPU usage hasn't changed much. So CPU is probably not a bottleneck, but the load on the disks, like the IOPS, the writes per second or whatever, increased quite a bit correlating with this, right? So in this case, what you would probably see is you'd have another graph over here, make this normal. This is like your, maybe we'll call it your IOPS. So that's IO operations per second. And then the graph, you know, it's a different shape here, but similarly, right? It was something where, okay, it was maybe you had like 1,000 IOPS for a while, right? Not too many, and then all of a sudden it jumped up to like 10,000 IOPS. So IO operations every single second. So that's the number of reads and writes happening on your hard drive every second. Okay, so you're getting this report. How do you figure out what the root cause of this is? And this is a big part of looking at the systems performance. Let's see if I can get it to focus there. Boom, right? Systems performance. A lot of it is, okay, I have a performance problem. How do I then go make it faster? How do I solve the problem? So there's a number of different things. Like one thing you might think here is, okay, like if you're naive about it, you might say, well, clearly, if the CPU graph, let's say blue was IOPS, and then let's say orange was our CPU. Okay, and then we're gonna go over here. So our CPU graph was like, you know, 50% CPU usage, whatever, and it actually didn't change when this IOPS thing spiked. So you go, it doesn't really seem like CPU is a bottleneck. It's something about the IO is a bottleneck, right? So the question is, you then start to inspect. You go, as the performance engineer, you go, okay, hey, database administrator or app developer, whoever's coming to you with this problem, you would probably want to ask, move this over here. You would probably want to start asking questions like, hey, did any of the workload change, right? Sometimes you deploy a new version of an application, it starts sending more queries, and maybe those queries are just reading more from disk. So is it actually a workload change at all? And in this case comes back, no, nothing about the app has changed, traffic is the same, the queries we're sending to the database are the same, nothing changed. Okay, so it's not an issue of like there's a new query or a new table in the database. It's all about the same, right? Did the size of the data change at all? Hey, maybe here the database was 100 gigabytes, and all of a sudden one day we doubled the size of the database, and now it's 200 gigabytes. So now it like, whereas before, maybe we have like 64 gigabytes of RAM. So before we had like a cache that was half the size of our database, whereas now the cache RAM is a quarter the size of our database. So now we're having to do more IOPS. Well, maybe they say, no, the database size is still 100 gigabytes. It didn't actually change in here, okay? So you're starting to basically go through, and there's like common performance problems that you can see and have to identify, right? So this is what we're actually going to tie this into the previous thing we talked about. If you're watching this as a YouTube clip, go find the other video where I talked about this. But when you're thinking about performance, you actually have to think about the entire system, not just, like, let's say this is Postgres. The problem might not be anything particularly in Postgres. The queries didn't change, the data size didn't change. You check if you changed any configuration options for Postgres itself. Like, did I change some of the like performance tuning characteristics? Nothing has changed there. So what you're starting to see is, okay, Postgres itself hasn't changed at all. The workload that is like, you know, the apps are sending queries to this Postgres server, that hasn't changed at all. So what is actually going on? And again, like one of the keys here is, right, okay, P99 has changed. If you actually looked at like your, let's say another thing that we could look at, we'll go down here and we'll start building some more graphs. Basically, we're going to build a little sort of Grafana looking dashboard, but right here in Excalidraw. So bring this down. Oh man, what's going on? Actually, let me group. I'll bring that down and I'll group this. Okay. All right. Is that there? There. Okay. So we've got the start of our little Grafana dashboard here that we're just kind of making up and drawing. So let's say, okay, like usually what you want to do is gather data, right? Sometimes this would actually involve going and collecting traces on your system. In this example, we're not going to get that far, but you can actually go and like take a trace of a Postgres query execution and then visualize that as a flame graph and look at that. But here we're going to assume like we're trying to solve the problem without having to go and do any custom tracing. We just want to use the data or the telemetry that we have already collected over the past couple of days to figure out the performance. So another graph we could maybe look at, and this is, let's call this Postgres P99, right? So our Postgres P99 went up, but maybe what we do is we look at another picture here, which would be, look here. What do I want to show? Your disk latency. So this is what is the latency of a disk operation that I'm doing, right? Over, again, the same time window, right? I know these are different sizes, but we're looking at the past week's worth of data. So the disk latency might be, again, low. It might be like 1/10 of a millisecond. I guess it depends. Whether that's low or not depends on if it's a spinning disk or a solid state disk, right? But it's like something very low, right? And then if this was, hey, suddenly the disk latency spiked, then it's like, okay, that might be indicative that there's actually a disk problem. But in this case, the disk latency didn't actually spike that much, right? Like all of the I/O requests are still taking 1/10 of a millisecond, 100th of a millisecond, whatever it is. So it's not actually, like this tells us it's probably not like the disk failing, right? The disk is still operating very fast for every single thing that we're sending to it. But what we clearly see is the number of IOPS is going up. So then you keep looking at things. And one final graph that you might look at, depending on what data you're collecting, is, just zoom out here. We move this up here, move this graph. I'll group this together. So the one final graph that we're going to look at, which will help us like identify this problem, is really not so much of a graph. I guess we could visualize it as a graph, but you might look at this other ways, is something like number of procs on system. So perhaps one of the things that you monitor is like you run top, right, which tells you how many processes are running at a given time. And it, of course, gives you a breakdown of what the process IDs are and what each one was and how many resources each one is using. So perhaps you have in your system something that is logging that every second, every 10 seconds, whatever, and reporting on this. So, of course, we could drill down into the specifics of exactly what's running. But if you see something like this, hey, prior there were 50 processes running on the system, 100 processes running, and then right around that 2 days ago, all of a sudden now, there's 10 or 20 or 30 new processes that weren't running before on the system. Okay, so this is probably indicative of some kind of issue. We're going to go and drill into what is the delta between what happened right there and then 5 minutes later, 10 minutes later, whatever, what does the set of processes look like over here? And then in this case, we'd go in, and in this particular example, what we're going to assume is there's some other application that started running on this system, right? So maybe some other team within your organization, maybe one of your engineers, whatever, let's say started running another instance of the database to do some testing, right? But instead of using an isolated test server, spun up a new Docker container or whatever, however you're managing your software running on your system, but spun up a new Docker container. And so you have your Docker container with your production Postgres server running, but there's also this test one running that has test load being going to it. And if you think about this, it's like, okay, it's just another Postgres instance, But if this new Postgres instance is now consuming some of the RAM, so like before we had, go over here, right? I'll just scroll down a little bit. So if we have, just make it a big wide thing here. So if we had 64 gigabytes of RAM, like I said before, usually there's some amount of this that is reserved for like the operating system, right? So the operating system, the kernel, et cetera, is going to need to use some amount of this RAM for things. Of course, there might just be, I'll just categorize it as other apps, right? So there might be other applications running on this system that are, doing monitoring, exporting logs, all of this kind of stuff. But then the majority of it, you would want to be given to your, your prod Postgres, right? So of the 64 gigs, maybe, 10 gigs are being used by other things, and then there's a few gigabytes being used for some of the like metadata of Postgres, but maybe you have like the total amount of RAM that Postgres can use for caching data at 50 gigabytes of this 64 gigabytes that are available. But then if you all of a sudden throw this other like test cluster in there that is going to be using some of these resources, change the size of these. So now your prod will just say that it's like splitting it in half now, right? So you have prod using 25 gigs and your test cluster using 25 gigabytes of RAM. All of a sudden, even though nothing about the workload changed, really nothing other than just how much of the RAM, particularly like the file system cache that your OS has that allows it to cache pages that Postgres needs from disk, if all of a sudden that has been cut in half, even though nothing else really changed, that would explain, well, now I have much less cache. So presumably, with the same query load, I'm going to actually have to do a lot more I/O operations. And that's correlated from happening the same time as this other test database cluster started executing on my system. So this is a problem, right? And this goes back to that diagram we were looking at before, which is sometimes the issue is your application sending requests changed queries. Sometimes the issue is I need to reconfigure Postgres to tune it better to use, to tune its various knobs that, there's lots of different config options on most databases that you can tune performance, or maybe it's the hard drive going bad or whatever. But in this case, it wasn't Postgres, the prod Postgres' cluster's fault. It wasn't the client's fault. It wasn't the failing hard drive's fault. It wasn't the operating system's fault. It was another engineer who happened to be running something else, but there's only so many resources on a computer, so then that impacts the capability of the main Postgres database. So I know that was a contrived example. That's basically the same example that is used in this chapter, which is what we're going over, right? So if you read that chapter, you'll see that. But this is the kind of thing that just like gets you thinking about how complex performance can really be on these systems. There's so many different things to take into account, so many different things to factor. This is a part of the reason why, not just with databases, in general, sometimes people prefer to use some sort of managed service for running, whether it's databases or queues, like your Kafka queues, or just your app servers, right? Your analytics databases, all of this kind of stuff. Because in a managed service, it's somebody else's, you're essentially offloading the burden of lots of things, the server management and capacity planning and all of these kind of things, capacity planning in some cases, but also performance. Like, sure, you care about performance and you might tune your database on a managed platform or tune other aspects of the server, but ultimately you're trusting that whatever company is running this managed service has actually thought through all of these different complexities of performance, or if there are performance regressions, that the managed service, the people within there, will investigate and solve and improve the performance of these systems and not let bad performance go unchecked, right? Some of that onus is on you, the database operator, right? To build the proper indexes, send the right queries, right? Like some of it, of course, is the customer's problem. But in terms of all of these system level things, right? Like that's something that the experts who are managing these databases should be trying to optimize and make perform well. So that is just a fun little case study from the book, Systems Performance, that goes over one of many possible scenarios of how finding the root cause of a performance issue can be challenging, and it takes really thorough investigations and looking at data to identify and then go solve those problems. So there we go. That was fun, building a little Grafana dashboard right here. Let's see. Back there, yeah. I guess the one other thing we wanted to talk about was flame graphs. The only problem is I had like that little tool that I was talking about for visualizing flame graphs, and I did not really get to, it's been a while since I've used it, so I need to sort of relearn basically how to use it. So what I might need is just a second. I have a terminal off screen here to like get this up and running again. Let's see. So do I already have, okay, so let me move this over here and go back over here. Okay, so you can see that. Let's look at this. So just hang a little bit, ask questions, let's chat, but I'm gonna just try to see if I can get, Again, I hadn't just looked at this tool again, so I kind of forgot the best way to use this here. So do I have any? I think what I actually need is to... Oh, okay, so I already have... Okay, so maybe what we'll do is instead of running a new trace, we'll just look at existing traces. So then... the way that I would run this, how do I just look at an existing trace in the artifacts? What? Is that not what this was called? Artifacts. This is one of the cool things about AI. I probably should, actually don't even know, what does the README say here? It's kind of fun to be able to just, even if it's a tool you built, to be able to go to AI and just be like, how do we do this? Okay, but it is in the README, great. AI probably helped write this README. Collect a flame graph. Well, and this was a augmentation of an existing tool. So some of this might have already been written. How do we view this? Oh, did I make it so that, I think I actually have to run a web server though for this. Okay, so. Open viewer index. So I think the problem here is, oh, it actually, why don't I need a web server for this? It's actually crazy. Okay. Yeah, so that does actually work. Cool. We'll talk about flame graphs here in a second. Let me go back to stream and see what we got here. What time is it? Okay. So I missed a couple of the questions from earlier. Any real life performance issues that you faced that were really interesting? Hold on. Let me open up. Where is that flame graph viewer? I'm just going to get this open in browser here. so that we have something fun to look at while we're chilling. Okay. Any real life performance issues that you face that were really interesting? I mean, with databases, it's kind of interesting because there's honestly like so many different things performance can be, and this is one of 1,000 reasons why databases and data systems and data pipelines are so interesting, is because it's like, is the slowness coming from the network? Is it coming from the way the database is tuned? Is it coming from the underlying hardware not being good enough? Is there a disk bottleneck? Is there a CPU bottleneck? So a part of the fun is like doing the investigations. And so we went through that like example scenario from the book. Yeah, any that I particularly faced? Nothing that I want to talk about on stream right now. But that is a very good question. From my experience, many companies after facing performance issue decide as first to add a cache or indexes. Yeah. Sometimes the easiest thing to do is to add another layer to make the performance faster. And it all depends, right? Like if what you're trying to do is not add more components to your system because you're trying to optimize cost or something, then yeah, you probably don't want to just throw a cache on things. But in some cases, the cost of some extra caching machines is nothing compared to the money that you will make by making your system faster and therefore making your customers happier. So it's a no-brainer to just like, yeah, if we can add a cache and this will solve problems very quickly for our customers, then great, let's do it. Sometimes it's a combination of multiple things. So it just all depends. All right, so we're going to talk about, I think the last thing we'll do, how long have I been streaming? Almost 2 hours, sick. I think the last thing that we're going to do is talk about flame graphs. So let's do that. But particularly, I think I'm going to actually change my view a little bit here. So can I go to this view? Yeah. Let me look and make sure that this looks good there. Yeah, okay. Okay. Let's see here. Flame graphs are a really powerful and kind of fun way to visualize the performance of something and basically what a piece of software was spending its time doing while executing. And a byproduct of that is it's a great tool to investigate if something is running slower than you think it should, and you want to optimize the performance by using better algorithms, implementing your software better. So how do these work, and how do you use a flame graph to make performance better? This here is a tool that I augmented from something someone had online for visualizing flame graphs, for doing flame graph visualizations. Flame graphs, my understanding is, were first sort of invented by Brendan Gregg, who's the author of... So my understanding is... So flame graphs were first invented by this guy, Brendan Gregg, who's the author of the Systems Performance book. And a number of other people have used them over the years to look at and analyze performance of program executions. So what I have here, I'll talk through kind of what this is doing and how it works as we go. But this is a flame graph. And what a flame graph is, okay, in order to visualize data, you first need to have collected that data. So what data is a flame graph meant to be visualizing? Well, the data is generally collected from what would we call it? I guess would a trace be the right way to, actually, there's two different, I just don't want to get my wording wrong because everyone on YouTube will, correct me. Yeah, I guess it would be more of a profile rather than a trace that we would use this for. So generally for a flame graph, what we're doing is we're visualizing the results of a program profile. That sounds terrible. What we're doing with flame graphs is we're visualizing the results of profiling a program. And basically what profiling a program means is we ran a program. Maybe it's a database like Postgres, or perhaps it is a video game. Perhaps it is, oh, what's going on here? Add effects using hand gestures. Oh, no, thank you. So some program, and we want to assess the performance of it. Maybe we're just curious, or maybe we know, hey, something seems wrong, something seems too slow. So what you do is you start executing this program, and then you collect a profile. And more or less what that is doing is it'll have a sample rate. So it could be once every millisecond. It could be once every tenth of a millisecond. It could be once every 10 milliseconds. It will basically collect a snapshot or a sample of, at that moment in time, what was the program doing. Particularly in this case, it's essentially what was the call stack. So if you're familiar with how software works and programs are written, right, you have functions, and those functions can call other functions. And so as function calls are made, right, you have like your main function, and that will call another function, and that will call another function and another function. So we think of that as our stack of functions, and then as functions return, they will be popped off the stack. And so what we're visualizing here is a bunch of samples of, at this point in time, this is what the call stack looked like, and then we put it on an XY axis, right? So the horizontal axis here is basically representing time passing, and what did the stack look like at any given point of time. So this is one flame graph. And what we look at is we can see, okay, like Postgres, this function routine or whatever, actually a few up here, we have main. So I have this when I hover, we can see those kind of things. Maybe I should, I guess zooming in will be a little bit hard here. We'll do this. So anyway, this function here is the main function. And so let's see. I guess like the problem with this is the way that I'm looking is it's like flipped. I'm going to actually change the way that I'm going to just go up in the corner here, and then I'll make this go full screen again. And then will it help if I zoom, or is that still too? I guess I can zoom to this level here. That looks pretty good. Yeah, okay. So in the flame graph, each one of these layers essentially represents a function that we were in. And you can even see like main down here, right? Throughout the whole collection period of this execution, main was on the stack. And this particular program profile result was profiling Postgres as it was executing a particular query. And so you can see a lot of these functions that were essentially running the whole time are related to Postgres, right? We have our Postgres main, portal run, all of these kind of things. And then it gets more interesting basically once you get above these initial layers here. So we can, with this tool that I built, we can drill in and look at, okay, I want to look at just this section, what was happening here. And so now we drill in, we get rid of all of those functions that we know are already running at the bottom. And we can see that the base function that was executing through this whole thing was an exec scan. So this was probably a function to handle doing a scan of a bunch of data, right? This is a Postgres query, and then doing something with it. So we can see above it, right, there was a bunch of like MD5 text. So some hashes were being done apparently, right? We have these crypto hash functions. So essentially we can look at and see like this horizontal line here for MD5 hash is indicating how much time did I spend in this function, and then that function called a bunch of other functions and so on. And we can also see by zooming in over here, libcrypto. So this is a library that Postgres must be relying on, a Unix system library. And so we spent a good amount of time in libcrypto, right? And so if you had a concern like, hey, maybe libcrypto is too slow for my application needs, by looking at this, here we're very zoomed in, but we could zoom out and see, well, the grand scheme of things, this libcrypto function, again, looking at the whole horizontal axis, this distance is about, whatever, 10% of this full distance. So probably at most, libcrypto, like if we optimized it to 0, the best we would get is like a 10% performance improvement. So if we're thinking that there's some deeper performance problem, it's probably not libcrypto's fault, right? Okay, so then we go over and we kind of see like after this MD5 and this exec scan finishes, we go into another phase, which is we have this exec check index constraints. So while executing this Postgres query, there was some overhead in checking the constraints on an index. So I don't know the Postgres internals and all the function names and stuff like that very well, but perhaps this is the schema of this database had some tables where there were constraints, like perhaps on foreign keys or something, and it spent this amount of time checking, right? So we checking constraints. We have a number of functions for getting identifiers, right? And yeah, so that probably had something to do with enforcing constraints, and that took up 25% of the execution time. And this would be something interesting to consider if we do prove like, okay, that exec check index constraint function was basically just enforcing constraints that I put on the database with my schema, and I really wanted to make this query run faster. One possibility would be, well, could I actually get rid of these constraints, right? Maybe I don't even need Postgres checking index constraints on this query. So if I change my schema to get rid of those, maybe now these queries will go faster. But that's just one thing. Okay, so then we kind of go into another phase, exec insert index tuples. And so I guess we're doing inserting rows, maybe one row, maybe many rows into an index, right? And so there's a bunch of these functions relating to inserting records. There's like a big stack of things over here. So what's going on here? So this is a lot of, looks like functions relating to actually writing things either to the write-ahead log or to disk, right? Because there's a bunch of functions that we're calling that are doing like file write iterator, things like that. So this has to do with actually updating the index. We can kind of zoom in here and see what's going on here. We have a heap insert going on here. So this is actually inserting things into our perhaps our heap file. Postgres, like the main files that Postgres stores rows in are known as heap files. So that's what's going on here. And we could drill into different components of this. What's all the time being spent on over here? Like there's some PG fsync. So some amount of time is just waiting on the fsync to complete to ensure that things are written to disk. So even without being a Postgres source expert, which I am not, but if you know generally about how databases work, how Postgres works, you can actually go in, and this is one of the reasons why naming functions well and accurately is so important, that I can get an idea of how much time while this query was executing in Postgres was spent doing an exec scan, how much time was spent checking the index constraints to making sure I wasn't breaking any constraints that I asked Postgres to enforce for me, how much time was spent updating the index, how much time was spent actually updating the rows in the table itself. And so this is something where the first step before getting a profile or getting a flame graph like this is you have to go collect the profile. So you have to have, which we're not getting into in this video, but you have to have the right tooling on your system set up to where you can execute Postgres while it is grabbing these in very tiny increments, these rapid sort of visuals of like at this moment in time, here's what the stack looked like. And then once you've collected it, then building a tool where you can visualize it. And in this case, we have the ability to really like zoom in a particular part and see what's going on. So looking at it at this level of detail is useful in multiple ways, right? So this level of like looking at how much time was in every single one of these functions is probably more useful for someone who's actually like a Postgres maintainer, right? Who literally is spending their days building, like writing the source code for Postgres, doing testing, doing performance analysis, figuring out how can I make some of these functions faster? How do we make the performance of Postgres better? Because that person is probably pretty familiar with at least some of these subsystems of Postgres and can go in and say, oh, the xlog insert record function was taking a lot longer than I thought. Maybe I should go in and like, maybe I don't need to be doing this call over here, this call over here, or whatever, right? For someone like me, who's not a Postgres maintainer, but if I was a performance engineer at a company who was asked to help with a slow query performance, even though I may not go in and change the source code of Postgres, this can still be very interesting to just get a good sense of, here's this complicated query. And by the way, in tools like MySQL and Postgres, you can ask them for query plans, which basically gives you like a higher level tree outline of the plan of how it's going to execute the query, and you can get statistics from that. So in some cases, just the query plan from Postgres is probably enough. But if that wasn't enough, and you really needed to know, like, is libcrypto taking too long, right? Do I need to, like, whatever, update libcrypto to the newer, more efficient version? Or like, hey, where was it when we were over here? There's a lot of time being spent in, I guess it's not that much time, right? So this, in the grand scheme of things, this is pretty small. But if there was a lot of time I noticed doing fsyncs, it's like, well, I probably want that. But if I was willing to trade off data durability for performance, maybe I should like disable the fsync requirement on Postgres. Dangerous, because you don't want to lose data, but maybe this is a system where it's fine if like occasionally a little bit of data is lost, if this is just like for you know, user click tracking or something like that, and you don't care about data durability as much. So anyway, this tool can be useful for a number of different kinds of people, depending on what you need, how detailed of performance information you want. Flame graphs are an awesome tool for inspecting and looking at this kind of stuff. So there we go. That is flame graphs and profiling. Lots of fun. So questions. I'll hang out for like a few more minutes and then we'll wrap it up almost at a 2-hour stream. I usually do between, say, like an hour and a half is usually what I do. So this is a longer stream than what I usually do. But it's been a fun one, and I hope you guys are enjoying. So maybe should just remind you, the book is a little pricey. It's like $60-ish. But if you want to follow along, my plan is to possibly go through this whole book, possibly just going through some of the chapters that are a little bit more relevant because it's a long book. But the plan is over the course of the next couple of months to do some streams on some different aspects of system performance, kind of using this book as the general guide for what to talk about and what material to go over and so on. So what I will do is over the course of the next couple of days, I'll read chapter 2, and then we'll do another stream next week, and we'll talk about chapter 2, and we'll go through and we'll have a lot of fun doing this. So I guess what I will say also, so if you get this far into the stream, you probably are interested in the stuff that I do, and I know some of you are already watching on YouTube anyway, but in case you're not watching on YouTube, you can go subscribe here, youtube.com/@BenJDickin. Technically, I also stream this to LinkedIn and to X and to Twitch even. I don't think many people watch on Twitch, but I technically do stream this to Twitch. But probably the best sort of go-to place would be YouTube, because that's where I keep the streams up. That's where I post the clips later on. So if you like this kind of stuff, whether it's databases, performance, distributed systems, consensus algorithms, all these kind of cool computer science scaling systems things, sharding databases, you should go subscribe over there. You should also go check out PlanetScale, of course, because we do high-scale databases, sharding, and if you follow me on X, of course, you'll know that I talk about that kind of stuff sometimes too. But yeah, so go check this out. Go, subscribe, or you can look at some of the old streams. Let me pull this up just on stream, and I'll show you around. Yeah, so like I have, actually, let's look at the playlists here. I've got 2 different playlists because last year we went through designing data-intensive applications. I was a little bit newer to streaming back then, so there's some audio quality issues and whatnot in some of them, but good stuff. And then we also went through database internals, so you can go back and look at the old live streams. And also I go and I will like clip the videos. And so if you just are like, hey, I just want to spend 10 minutes learning about database sharding, or learning about the Paxos distributed consensus algorithm, or learning about LSM trees, right? Like I've got a bunch of content on here. So go check it out, like, comment, whatever you want. Or if you don't like it, don't comment. But just so you know, it's here. And if you like what we did on stream, go hang out over there. All right, cool. Well, thank you, everybody. Did we get to 2 hours? Almost there. Almost at 2 hours. Boom, 2 hours. Okay. Well, thank you, everybody, for being on the stream. Yeah, so unfortunately, I am about to sign off. So the stream is almost over. Cannot comment on X IDKY. I'm not sure. Yeah, I don't know. I don't know if maybe you have to be following. I'm not sure if that's true. Make sure you're actually logged into your account. How often do you stream? Where's any calendar? So I stream about once a week. There might be some weeks where I do it twice a week. There might be some weeks where I don't do it at all if things are busier. There might be some times where I go 2 weeks without streaming because of life going on. But anyway, the way to know that I'm doing it is you can subscribe and hit the notification bell on YouTube. But also on X, I try to let you know ahead of time. I don't always do that. Like this morning, I only posted 2 hours before. Sometimes I post the day before. But also occasionally I just stream without telling you. So it's a little inconsistent right now. We'll see if someday I can get more consistent. But for now, it is what it is. All right, everybody. Thank you for watching. We will do another stream next week. We'll leave with this comment. Very nice. Thank you so much. You are welcome, a LinkedIn user. And I will talk to you all in the next